Welcome to April 18th LeetCode Challenge. Kth smallest element in a binary search tree. Given the root of a binary search tree and an integer k, return the kth smallest value, one index of all the values of the nodes in the tree. So we're given the example here of this binary search tree 3, 1, 4, null 2, and we're given the first, we want to find basically the first kth smallest value. So the first kth smallest value, one index, would be 1, because 1 is the smallest value, and therefore return 1. Similarly, we have example number 2. We have this binary search tree as such. We wanted to return the third k smallest value. So the third k smallest value being where k being 3, we have basically 1, 2, 3, index at 1. Therefore, the third smallest value will be 3 as the output. So the constraints of the number of the nodes in the tree is n, and k is greater than or equal to 1, which is less than or equal to n, which is less than or equal to 10 to the 4. We have the value of each node is between 0 to 10 to the 4. And we have a follow-up question here. If the binary search tree is modified often, so we have an insert and deletion operation, and you need to find the k smallest frequently, how would you optimize it? Well, there's two kind of approaches we can go about this. There's a bunch of hints as well. The first one we decide is how do you traverse a binary search tree? There's a depth first search and a breadth first search. Essentially, a depth first search, we just basically go to the depth as a priority. We just start from the root and then reach all the way down to a certain leaf, and then back up the root, and then reach another branch. That's essentially what a depth first search would be. A breadth first search is that we scan through the trees level by level. So level by level, like this, and then we just basically do So we are actually going to do a depth first search, and specifically we're going to do an in order traversal. So now that we have decided how we're going to traverse the tree, next thing we're going to decide is whether it's going to be recursively or iteratively, because a binary search tree you can kind of do both, and usually both of them have different time complexities. So it's very straightforward with a recursive case. The idea kind of basically using an in-order traversal of a binary search tree, put it into an array that's sorted, and then we just ascend in ascending order, and then we just return the kth minus one element in the array. So it kind of works like this. Let's define another function here called in order, and that is going to take a r, which is going to be like a root. So from this, we want to return basically in order r dot left plus the r dot value plus concatenated, I should say, in order right, r dot right. If r else return empty or null. And then basically we want to return the entire, so the k smallest function here, basically what we want to do next is call the in order function, and we call it with the root inside it. And then we want to take the slice of the we want to return the k minus 1 position. Let's run this code. Okay. So this should work. Awesome. It's not the fastest solution, but it'll work. It's kind of neat though, because we have kind of one-liner and a function inside it. So time complexity wise is big O of n because it's built in a traversal, the in order traversal, and it's recursive. And the space complexity is also big O of n because we need to keep that in order traversal as well. So that's one way of doing it. Let's aim for the more interesting way, the iterative in order traversal. So similar to the recursion case right here, where we would build the stack or the list, or the array I should say, we can speed this up actually by, there's no need to build the entire in order traversal, so we don't need to build the entire thing, we can just stop whenever we find the kth element. So let's kind of do this again, but this time we are going to do a couple of, what about stack? So the first one is a stack, and it's going to be an empty array of course, and then while true, and while the root exists, what we want to do is append to the stack the root. or append the root to the stack. Alright, and then we want to update root to be root.right, no, root.left. Then we want to take it from the left side first, and then basically that's pretty much it. We update root, and every time we just append the root each element to the stack, and then we just keep on updating root until we exit the loop. Once we exit the while loop of the root, you want to basically make root be the stack.pop, which is going to take the last element of the stack. And then we also want to decrement k, because we want to find what the smallest term is. So next thing we want to do is we take the last element. Now we have decremented k by 1. We want to know whether it's whether it is a kth element or not, right? So if not k, then what we're going to do is return root.val, because k is now a 0. That means that the last item popped from the stack is the kth smallest value, index of 1, of course, of all the values in the node of the tree. Otherwise, what we need to do is update root to be root.right. And so therefore, just pop from the stack again. Let's run this. Alright, submit the code. This should be quicker. Yep. So this is time complexity is actually the height of the tree plus the k for time complexity, because the height of the tree being the stack, and plus the kth element, which is this before popping it. So every time we append to which is the height of the tree, and then we pop it each time plus k values, right? That's time complexity. And space complexity is obviously the size of the stack or the height of the tree, which makes it big O of n worst case, or big O of log n being the average case for a balanced tree. The tree is balanced. This is not a balanced tree, but yeah, that is pretty much it. Alright, have a great day, guys.